As been remarked several times, so Antonio Misevich was interested in many things. So in particular, like part of his interest was in com computation complexity and things convex. In particular, he was interested in various generalizations of or extensions of some remarkable polytopes, such as the Burger von Neumann polytope, the polytope of doubly stochastic matrices. That's already been mentioned. So those polytopes generally even more complicated, and even the simplest questions and most fundamental questions about them, like volumes, the number of integer points there, the number of vertices for some extensions, are pretty hard. So, but of course, when you look from point of view of asymptotics and approximations, things kind of become a bit easier, right? And I'd like to talk about some work that I've done over maybe 10 years now with by myself, also with co-authors, most notably with John Hartigan and Mark Rudelson. And I hope that Antonio Message would have liked it. Yeah. So here's the first problem that I'd like to think about. So um, suppose I have a polyhedron defined by a system of linear equations and coordinate inequalities. So it basically, geometrically, is just what? The intersection of non-negative portent with an affine subspace. But since I'm be interested in computing, so I'd like to think in coordinates, just numbers do not lie, right? So then the matrix is of the full rank here, right? So it's an n minus m dimensional subspace, affine subspace. And suppose that the polyhedron is bounded, has non-empty relative interior, which means that it contains a point where all coordinates are positive, strictly positive. So the first goal is to, can we actually, from this data, can we approximate maybe somewhat crudely, but quickly, the volume, right? That's the n minus m dimensional volume because the dimension, of course, of the polytope is n minus m, right? So, of course, so in general, computing exactly is pretty hard. And if we go into kind of computation complexity theory, then in some sense, exactly, you cannot do it faster because you can argue that even to write the answer, it will take you like exponential time. But once we are talking about approximations, things become easier. So there are randomized methods like Monte Carlo simulation is the most efficient, and that was a great progress in the 90s. But here I'm more interested in a formula. Just can I write a formula for the volume? Uh, well, not exactly, but something close to the volume. And then I look at problems that are even more complicated. So can I relook at the number of integer points there with 0, 1 points? So, and if there are no objections, then that's a problem I'd like to discuss. All right. So, yes? No? Okay. Yeah, so please feel free to voice objections or questions or, you know. So, so I'm building towards that formula. So, what we need, I need a very special point in that polytope, and the whole formula will hinges on that point. It actually has a name. It's analytical center. It's the point where the sum of the logs is maximized, and of course that's a unique point because the sum of logs is strictly concave, right? Something like this. And I add the dimension just because things become kind of more meaningful with that. So it's kind of interesting that this point, yeah, it's really easy to compute because you optimize a convex function, and also for polytopes that have a rich symmetry group. Sometimes you don't even need to compute it. You just know what it is because it has to be invariant under that symmetry group. So I think the first time I saw that in print was in James Rangar paper uh, in 1988. And so it was at the source of so-called interior points methods in linear programming. So it was a kind of a benchmark thing that easy to compute, right? And with that point, I can write the formula. So here's the formula. So again, so we have a bounded polyhedron defined by a system of linear equations and coordinate inequalities. So it's the intersection of an affine subspace and non-negative 4/10. So somewhere inside, there is this point. And what we do, so we construct another matrix B from the matrix A. So how? We just multiply the column of A by the coordinate, Z sub j, the j's column. And then that's the estimate, right? So e to the n, e is just the usual e, it's 2.71 and so forth. So the product of the coordinates of the analytical center and times the ratio of two determinants, square root of two determinants. So in the main result, which is joined with Mark Rudelson, is that it approximates the volume with an effector which is exponential in the codimension, right? So gamma is some absolute constant. And right, so that's what it says. So in particular, if the polytop is polyhedron is defined by like a fixed many equations, then you approximate within a constant factor and so forth. Right. So I'd like to then explain where the formula is coming from, but that's the approximation that we'll be working with. So just one quick remark that, of course, you can. So the way it's written, it's kind of coordinate dependent, right? So the same affine subspace can be defined by many choices of linear equations, but of course the ratio of the determinants will not depend on a particular choice. And the other thing is that it scales well, right? So as the volume should. So if you kind of dilate your polytope by a factor of tau here, right, then the volume gets dilated by what it should be, right, by the that constant to the dimension. Okay. So I'd like to, of course, illustrate that it's not completely outlandish. So how does it work for a simplex? And for the simplex, we have just one equation, right? And so all the coefficients here have to be positive because it has to be bounded. And of course, I can scale that equation to the right-hand side n just because, I mean, it doesn't matter really because the estimate in the volume scale accordingly. So then the analytic center is not very hard to figure out. It's just the reciprocals of those coordinates here, right? And the formula, the estimate that we get is this. But we all know how to compute the formula for the simplex, right? So we know exactly so. And if we compare the two, we notice that indeed it approximates within a constant factor because of the Stirling's formula. So the true value of the volume is roughly 1 over square root of 2 pi. And that 1 over square root of 2 pi is not accidental. So the estimate that I advertise approximates the volume within the factor 1 over square root of 2 pi. And somehow, so going back to the formula, so it knows at least something about Stirling's formula, right? So basically, the way we compare the two approximation is through the Stirling's formula, and the approximation that I'm talking about captures the true value, right? Uh, up to that square root of 2 pi, which is not accidental, right? So that's the example, one example that shows that the formula is not a complete nonsense. So, there are any objections?
Is it in general easy to compute this analytic center?
Yeah, so that's the whole point, right? So that's what we started with. It's a benchmark problem for so-called analytic, so-called interior point method. Yes, it's very easy. Yeah. So basically, what you do the quickest descent, right? So it's a concave function, or ascent, right? So you go up the gradient, right? And you're quickly there. So okay. So then, that's not exactly very exciting to get an approximate formula for the volume of the simplex. And here's the polytope that Anatoly Message really liked, the polytope of the doubly stochastic matrices. That's also known as Berghoff von Neumann. Oh, von Neumann, right? So although the papers appear within 10 years of each other. So it's a polytope of, we call it, I kind of used standard letters for dimensions m and n, so we call it R by R matrices with non-negative entries where the all rows and all columns sum up to 1. Right, and that was also mentioned last time, yesterday by Mikhail Gromov. Right, so it's a wonderful thing. And then, so what the formula gives for that? So there is one issue here that we have two R equations, right? But they are not linearly independent. If you add all the row sums, then of course it's the same if you add all the column sums. So the codimension M is 2R minus minus 1, right? So the dimension of the polytope is R minus 1 squared. And then the nice thing about the analytical center is that we know it exactly, right? Because of the symmetry. What else can it be? It's the matrix where all the coordinates are the same, 1 over R, right? So 1 over R, right? And the estimate that we get is this. And some years ago, like 15 years ago, Canfield and McKay obtained an asymptotic formula for the volume. And if we compare it with the estimate, then we see that the factor is, so again, that's square root of 2 pi raised to the codimension, right? So it's really square root of 2 pi raised to the 2r minus 1. And then there is this somewhat mysterious, but I'll mention it. So coefficient e to is cubic root of e, right? And with John Hartigan, we called that type of approximation when the true value is actually close to that estimate that I advertised, but divided by 2 pi to the half of the codimension. So we called it the Gaussian approximation, and I'm going to explain why. Right. So again, so it fits. So and maybe one more example that's again, it's a kind of a generalization extension rather of the Berghoff von Neumann thing. So this time they have a name. They're called three-way planar transportation polydopes. So instead of square matrices, we have cubes, and they filled by non-negative numbers. And now the what I would call a skewer, right? The sum in every row, column, and however you call it in the third dimension is one. I prefer to call it skewer, right? So you can pretend that you kind of skewer it, right, with the lens or something, right? So again, so there are three R equations, but of course they are linearly dependent. So the true dimension is R minus one cube. And again, we don't have to do anything about the analytic center because by symmetry, it has to have 1 over R everywhere, right? And then we get the estimate. And what we know, it approximates within a factor exponential in codimensions, so within a factor e to the roughly R squared. So if we compare, we see that in logarithmic order, the error is certainly smaller than the true answer, than the estimate, so it's meaningful. And in fact, I believe that's the best that's known for this polytope. So we don't know an exact asymptotic, and we don't know anything more exact than that, right? So these are three examples. So we started with this. Sorry if that makes you dizzy. Yeah, we started with a simplex. Then we went to Berger von Neumann and to the doubly stochastic matrices where we know exact asymptotics. And then we went to some generalization, extension rather, where the formula that I advertised is the best known. Right. So any, again, objections? Okay. So here's the main formula, main theorem rather. So it basically gives you estimates on the constants, right? So probably not very interesting, but it's just to say that there is a result, right? So you can prove it that the bound that are advertised indeed estimates the volume within exponential factor. So we can improve these constant a little bit, but it's kind of interesting. So to have some constant, it's relatively straightforward convex geometry argument, which was known long time ago. But if you try to improve it, then it appears that you need more and more complicated results on the so-called thin shell estimate. That's great progress being made. But for us, it just only improves that constant. So that's also related, of course, to the slicing conjecture by Bourgain. So any progress there sort of improves the constant a little bit. But to get some constant, you don't need much. It's really some kind of general argument from convex geometry. And now I'd like to talk about the proof, the meaning of this formula, and also relate it to statistical physics. That's another thing that Anatoly Moisеевич was interested in particular in connection with combinatorial problems, right? And we heard about that too today. So again, anything we should pause and ask questions or comments before I go to the idea of the proof.
What's your intuition of what is really going on with gamma?
With gamma, that I wish I knew. I actually don't know. So, for example, if you ask me what's the extremal cases, I really have no idea. So somehow I doubt that it goes as far as the slicing conjecture. So I really don't know. Yeah. But I'd like to explain the general idea, right? So we need probability. So we all know what a standard exponential distribution is, right? So that's this density function. And then there is a simple theorem, which, formally speaking, John Hartigan and I proved, but I mean, it's just a Lagrange multiplier computation. So if you have a standard exponential random variables and you scale them by the analytic center, so you get a vector of independent non-standard exponential, then it's just constant on the affine subspace, the density. Right? The density is constant on the affine subspace. And the proof is the exercise of in Lagrange multipliers, but there is a deeper reason which kind of connects it with statistical physics. So this particular distribution has a constant density because it's the largest entropy distribution among all distributions supported on non-negative fourth-tenth and in the expectation in the affine subspace. And why would it have a constant density then? So because if it doesn't have a constant density on that affine subspace, you can reapportion it, equalize on that subspace, and then the entropy can only go up, right? So it will have to have. And what's the relation with statistical physics? So in some sense, you can argue that that's the inspiration from statistical physics. So that goes back to works of James. So I forget, in the 50s, 60s, right? So who wanted to find the very few axioms that would sustain statistical physics. And so his main idea was that if you have a distribution from some unknown distribution from some class, then you should assume it's a maximum entropy distribution from that class. Because, well, from a physical point of view, so if it's some class, you know something about it. And you don't know anything else. And the reasons you don't know anything else is that you're not supposed to know. And that means that, well, it's maximum entropy. So just a quick illustration that why the expected, why the distribution of the squared of velocity of molecules of air in your room is Gaussian, right? Because what do we know about that distribution? So if there is no draft, it's the only thing we know is the temperature, which gives you the expectation of the square, right? Square velocity. And what's the maximum entropy distribution in the class of all distributions with fixed, with say expectation zero and fixed variance? It's a Gaussian. So it has to be Gaussian, and it is, right? So something like that we can try to pull here. So we pick a random point from a polytope, right? And what do we know about it? We know that it's non-negative and its expectation, right, lies in that affine subspace. So it stands to reason then, from that perspective, to try to approximate it by the maximum entropy distribution with that property, and that's exactly the scaled exponential, right? So, and then of course, a simple corollary of that is that if you take this scaled exponential distribution, you multiply the columns of the matrix, right? So you get the matrix B, you get a random variable. So then the volume of the polytope can be expressed exactly as the density of that random variable at its expectation. And that turns out to be enough to get that estimate on the volume. So why is that? Because what you know the expectation, and you can always assume that the covariance matrix is the identity matrix by changing your matrix A here. And then the last thing that you need to know is that this is a log concave random variable. So the density is log concave. You want it's isotropic, and you want to estimate its density at its expectation. And there are bounds for that. So for example, I did that for simplex here, then you can actually compute that density. That's exactly the gamma density, the sum of independent exponentials. And of course, yes, the volume is expressed in terms of the density of the gamma density at its expectation. Right. So it turns out, right, it turns out that, yeah, that's what I'm explaining here, that we have a log concave density. We're interested to estimate its value at its expectation. And we can always think of it as isotropic with covariance identity because we have a choice of choosing that particular matrix that defines the affine subspace. And so the lower bound for that density applies to all log concave isotropic density. The upper bound, so if the slicing conjecture had been proved, then we could have just borrowed the upper bound from there. But since there is a very little that, so we have like log something instead of constant. So we needed to do some work. And that work was inspired by theorem of Keith Ball about the largest volume of a hyperplane section of a standard cube, right? So by the way, so does anyone know what's the largest volume of the hyperplane section of the n-dimensional cube with side equal to 1 is? It's interesting to compare what different audiences are interested in. So the question is, so I have a cube of side 1 in dimension n. What's the largest volume of a hyperplane section?
In the middle?
So like what? Like perpendicular to the main diagonal? So okay, do you mean perpendicular to the main diagonal?
Yeah.
No, it's actually square root of 2. So you take any two-dimensional face and draw a hyperplane through that. It's kind of remarkable, isn't it? Yeah. So it's square root of 2. Yeah. So if you take this perpendicular to the main diagonal, you get less, and you can figure it out from the central limit theorem, actually, what it is for large dimension. Yeah, but for yeah, so it's always square root of 2. And we were sort of inspired by the proof of Keith Ball working with characteristic functions. But I should admit that Keith Ball proof is much harder. So we just got away easy. Right. So that's basically the idea of the proof. So for the volume and the volume formula, where it's coming from. So again, let's see, where's this? Again, I apologize if you feel dizzy. So that's the formula. So any objections? Okay, so I'd like to say something about more complicated issues. Oh, what I should have said, right. So where is this Gaussian formula coming from? Where is the square root of 2 pi? So as we discussed, so the volume can be expressed in terms of the value of the density at its expectation. And the thing is that the random variable is the sum of independent exponential. So it stands to reason that it's close to Gaussian. And then if it's indeed close to Gaussian, it's just a piece of cake to estimate the, we're estimating the value of the Gaussian density at its expectation by the local central limit theorem, and we get this formula. And indeed, this formula is much more exact in some cases where we can prove. In some other cases, we cannot prove that it's exact. And in yet some other cases, I suspect that it's not even true. That, for example, going back to that example with skewers, I suspect that the central limit theorem here doesn't hold locally. So we cannot, so the Gaussian approximation wouldn't work very well here. But I cannot prove it either. Right. So that's the best is now what's known as this formula. So right. So now I'd like to, in the remaining 10 or so minutes, I think 10 or so, right? So to count integer points. That's trickier because we know that even to find if there is an integer point, generally is what is called NP-hard problem, right? And so we cannot hope to get some as far as, for example, we got with volumes, but still we can do something. So this time, instead of the sum of logs, we consider this interesting function. So we assume that the polyhedron is defined by, again, as an intersection of affine subspace with non-negative portent, but the matrices and the right-hand side are integer. But now, instead of the, remember, there it was analytic center, log x. So we consider that interesting function. And why do we consider that interesting function? It's, again, the maximum entropy type of argument. So it's the maximum entropy of the probability distribution, which is necessarily geometric, which is supported on non-negative integer and has a given expectation. So we again playing the same game. So we have a polyhedron now, and we'd like to understand what a random integer point of that polyhedron looks like. And what do we say? So we say that, what do we know about this distribution? That it's concentrated on non-negative integers, and its expectation is in the affine subspace. So why don't we then apply Jane's principle and say that it's very well approximated by the maximum entropy distribution with this property. So the maximum entropy distribution supported on non-negative integers, non-negative integer vectors, and with expectation in the affine subspace. And we get a formula. So again, we maximize this. Right. So that's a lemma that basically says that if you rescale independent exponentials by the correct expectations, by the expectations obtained from maximizing the entropy, then you get discrete distribution on the lattice and was supported on non-negative integer vectors and with the constant probability mass function on the integer points in the subspace, right? So it's similar to the one that I talked about with exponential random variables, but here we're in discrete situations, so we take independent geometric, right? So properly attuned to the expectations given by that maximum of that function, right? And again, we get a vector, which is a random vector, which is the sum of columns of the matrix weighted by this random geometric. And we can express the number of integer points as the probability, the mass function that this vector hits its expectation. But in the discrete situation, everything is kind of much more complicated. So it's just some discrete random variable. It's not log concave. So it's some weird thing. The only nice thing about it is that it's a sum of many potentially independent random variables. So if we are lucky, the central limit theorem, local central limit theorem kicks in, and it will be close to the Gaussian. And then we again have to estimate the density of the Gaussian as expectation, which is a piece of cake. And so we get this formula. So this is an efficient formula, but the issue is, does it have anything to do with the true number of integer points? And in some cases, we can prove that it does. In some others, we cannot. But what is also true is that the experiments show that sometimes it's amazingly precise. And that degree of precision we are unable to achieve by by thinking. So we're unable to show, like to prove a theorem that it must be that precise. So here's some examples. So it's again so-called contingency tables taken from paper of Diaconis and Efron. So we want to count the number of 4x4 non-negative integer matrices with these row sums and those column sums. So why is that? Because that's a test of a correlation between eye color and hair color. Yeah, turns out to be. And here's the exact number of such tables. And Jesus de la Era computed the approximation for us, and it's off by 6%, which I consider to be pretty good. Yeah, so that formula gives you 6% error. So what happens here is that we say that we have a sum of 16 independent 7 vectors, right? And we kind of gamble that it's close to the, yes? It's close to a Gaussian. And that gamble, well, sort of up to 6% error turns out to be pretty reasonable, right? And here's another example also computed by Jesus de la Era. So this time we're working with so-called axial transportation polytope. So it's a cubic thing, but not, we are not counting, we are not fixing the skewer sums, but kind of planar sums over sections. So there are altogether 9 sections, and here are the sums, and we want to know how many non-negative integer arrays of that type. And again, we know the exact, that's kind of, that's the number. And the estimate that I showed approximates that number within the relative error of 0.2%, right? Which is much better. So why is it better? So again, we cannot prove anything that it should be that good, but here the random vector that we consider is the sum of 27 independent 7 vectors. So if we bet here that it's close to the Gaussian, it's a much better bet, right? Because here we sum up 16 random vectors, and here we sum up 27. So yeah, it should be closer to the Gaussian, and indeed it is, right? So that gives you 0.2%. Right. And that's pretty much it, what I wanted to say. So, yeah, I hope Darshik would have liked it. Yeah, he probably didn't see it, but So thank you.
Other questions?
A question, yeah. In these integer examples, how integer counting differ from volume?
Well, so in high dimensions, right, the volume and the number of integer points are often at odds, right? So if, again, my favorite example, take the unit cube, right? Then the volume is 1, but there are how many integer points? Well, 2 to the n, right?
Or
So,
zero. Or
what?
zero, you count with.
Or 0. Well, if it's standard, right, then it's, well, this, I mean, right? So, so the point is that in higher dimensions, the volume is concentrated around in the neighborhood of a boundary, right? And boundary of the boundary. So the volume is a generally poor estimate in high dimensions for the number of integer points.
But did you try it in these examples too? Let's compare. In
What?
this
Oh,
numerical.
in this example, that I don't know, but I'm willing to bet that it's probably pretty bad. Yeah, for the reason that I said that. Like, so volume estimates, as we know, the number of integer points pretty good. If in fixed dimension you start growing your polyhedron or convex body, right? And asymptotically in fixed dimension, right? It's the same. But if instead you grow the dimension, then, well, especially in this example, I would assume that, yeah, it's pretty close, like most of the points pretty close to the boundary somehow. Yeah, it's probably, yeah. I cannot say for sure. I didn't check, but I believe it should be off by a lot.
More questions? Let's thank the speaker again.